Okay, welcome again for the second part of the lecture series by Wei Li.
So now I'll give a definition of the and tomorrow I will start to discuss when this is a BPS algebra and the representations. So the algebra can be defined as you give me some generators and then the relations of the generators. So remember we have a quiver given by a bunch of vertices and errors between these vertices. So, so we label the vertices by A, B. So for each vertex in the Q0, there is three family of generators. So we use for the raising operator, we use E, A, and the cation. We use precise A and the lowering operators A. So a priori there can be infinite many. So we label them using say J. And then we can introduce a parameter to organize them in terms of fields. A priori, this J can take all the integers. But as we'll see later, for the E, this is actually just positive integers. For the precise, for the cation. So the range of this will actually depends on whether it's symmetric or non-symmetric. So generically, you'll want to take all the integers, but for symmetric, this is just a positive. And actually, there's also the notion of the shifted Yang-Nian, where you can have some numbers here, but to start with, we don't need to we don't need to discuss that yet.
So infinite, huh?
Say again?
There'll be infinite lowering operators, infinite cartons?
Yes.
For every...
Yes, I mean, a priori they're infinite. This is related to the fact that for the BPS spectrum, you also have an infinite number of states. I mean, this is supposed to characterize those states.
How should I think about this Z parameter?
I mean, right now you can, so this is, right now you can just understand it as a way to organize all these modes. I mean, similar to the VOA for the 2D CFT, you have the fields and the modes. Yeah, but I mean, there's also a more physical way of understanding that I can discuss more.
Okay. Maybe another question. Do I understand correctly that each copy for, let's say, fixed A and fixed J, this is like SU2?
For fixed J, it's actually more complicated. Okay. So you'll see, but I mean that's only for very special cases that they reduce as well.
Why is this term Yang-Nian? Yeah.
So the reason why it's called Yangyuan, I mean, it's a long history. So the first time we defined this was it's a generalization of this algebra called alpha Yangyuan of GL1. That's the uses plane partition as representation. So that it's sometimes it's a generalization of the. I should give credit for this. So this is defined by symbolic. 14. Actually, I think this also take the inspiration from all this paper by Feigin, Minwa, Jimbo. I mean, this paper about the quantum Toroidal algebra of GL1. So the first time we so this you can think of as the algebra for the type 2A string on C3. I mean, the first time we define this is for to generalize this to general toric labial. So that's why we call the quiver Yangyuan. So and then I shall explain later that when this quiver is the triple quiver of the thinking diagram of G. This quiver Yangyuan would reduce to the Yangyuan of G. So if this is just an ordinary algebra, it's a Yangyuan of that G. If it's a affine thinking diagram, it will be the affine Yangyuan. Yeah, that's why it's called the quiver Yangyuan. But for the generic quiver, I think it might be misnomer to say that it's really Yangyuan until you actually define all the coproduct structures.
And you're going to confine to symmetry quivers, or you can go beyond symmetric also?
Yeah. So this definition doesn't care whether it's symmetric or non-symmetric. But for this, if it's a triple quiver, it's by definition symmetric. Yeah, so the symmetric quiver, the property of the quiver Yangyuan heavily depends on whether it's a symmetric or not. There are many things that are different. But there are also, I mean, the definition a priori doesn't depend on that. Also, there, as you will see, at the level of just writing down quadratic relation is totally insensitive to the whether it's symmetric or not, and whether you have a superpotential or not. I think that's part of the reason why this is very convenient and useful, because it's you can think of it as a nice basis that it's a nice basis to do certain things. So yeah, so here I want to say that the symmetric is symmetric. For the symmetric quiver, this one has no negative modes. So that's also, I mean, for the Cartani, if you have if it's bounded below, that's also it's nice. For the racing and the Laurent operator, they are starting from. So we start from 1 plus 0 z plus. So this is the generators. So now we want to define the quadratic relations. So this is also, some people call it exchange relations. So for this, to define this, I first have to introduce a bit more stuff. So first, remember we have all these arrows. So for each arrow, I want to assign a weight. I mean, right now you can just think of them as some formal parameter. Let's call them and now, so if there are loops in your quiver and then there are superpotentials, so for each term in your potential, you will have that will give you a constraint on the weight. So that would be so this will call loop constraint. So after this, we're ready to define the most important ingredients of this in the definition of this algebra, which we call bounding factor. So for two vertices A and B, we define a rational function. So this is a notation. So for each arrow from A to B, you get a factor in the denominator. Sorry. For each arrow from B to A, you get a factor in the denominator. And then for each arrow going backwards from A to B, you get the numerator. So now we can define we can write down the quadratic relations. So first, the pattern, they are just all, by definition, they all commute. And then we have the EF relation. So that's already a bit similar to the question you asked about SU2. So this means it's a super commutator. I mean, it will be a commutator when they're both bosonic, and a commutator if they're fermionic. Okay, so you see these two relations doesn't depend on Q, doesn't depend on the quiver at all. So these two relations are universal for all quivers. And now we have cosine E. So let me just write down this the tilde sign and I'll explain what exactly it means later. So and then cosine F So this is the relation between the Cartan and raising operator. So now for the Cartan and the lowering operator. The only difference is that here in this factor, it will be the inverse of this factor.
Should I understand that this bonding factor gives us like the raising and lowering in some sense? Because you are writing here something like, I guess, like energy and raising operator in different orders. So it, in analogy to the standard SE2, it is like how the energy changes with the lowering and raising. And I'm not. My question is, how far can I go with this analogy in my mind? Is it a good framework for this? Of course, this is more complicated. I'm trying to.
Yeah, I mean, if you just look at this, it's roughly. But as you see, that one intriguing thing I find is that the E relation have exactly the same structure as the precise E relation. It's exactly the same. It's exactly the same structure. You can, I mean, you can draw it like this. So this beside A, E, A, E, F. Just E. So this is phi inverse. And then the FF is also has the same structure as the beside F. So this form would heavily depends on the quiver, and also so the E and F, they can be both bosonic or fermionic, or even more general. So there will be some signs here, or even phases here. But as a first order consideration, you don't need to care about it. So the information of the quiver will enter via this rational function and the sign here. So, what is this? So by analogy with VOA, so this will be like the OPE of the fields in the 2D CFT. And you know that sometimes you also want the relation in terms of mode. So also it's the same for us. We actually derive this relation first in terms of the fields, but very often you will need the relation in terms of mode. In particular, if you want to compare to other algebras. So it's actually important to also have the mode relations. So to derive the mode relations, so it's still quadratic. So I use this the mode expansion. So we first plug in this mode expansion. To those relations in terms of field, and then you expand, and then you take the singular terms. So, so the first two will be easy. They will just be and then for the next word, that will be slightly more tricky. So you first have to take this the bounding factor, and then you write it as it's a rational function. So you write as the numerator divided by this denominator, and then you move the denominator to the other side. So, for example, let's take the side psi e. And then you expand. And then you take the singular terms. So that's why it's more useful to think of all these h's as a formal variables. You're not supposed to cancel them, even if you see some factors.
It depends on the arrow, AB arrow or B.
Yes. So when you're doing this step, you're not supposed to cancel any factors, because ultimately you want the mode relations.
So the reversing the arrow will be numerator denominator will get exchanged.
Sorry.
A to B, if you make it B to A, then it's the numerator and denominator will get, numerator will become denominator, denominator will become numerator.
Yeah, but recall that there's also the sign. Yes, the one. There's this relation here. I mean, there's also this minus sign there.
I see.
I mean, from the definition here, you have this is a plus and this is minus. Yeah, so this is a relation that's important for some distances. Sorry. Let me write it here.
Equation is fine.
Let me write it here. So as you can check, I mean there can also be some factors here that I'm ignoring here. But in the end, you want to, I mean these factors, in the end you want to fix it such that you have this. So this is actually important for many purposes. Okay, it's better. What would be a good example to So let me give some example for this bounding factor. So so remember that we listed some example for the quiver in the morning. So the simplest one is the quiver with one vertex with no loop. So when there's just one vertex, then I would just not write any labels for this A here. So we will have this one, but I will just, because there's only one, I just ignore this. So that's one. And for the Jordan quiver, so there's one arrow, and we give it a weight h. So then there will be. So you just look at this definition here. And then if you have M loops,
So wait.
So the weights can be different. Sorry.
I just want to use this part.
Yeah, but let me make what first.
I want to keep this side.
Yeah, I have it. Okay.
Sorry.
The weights can be different on an M loop or can be same.
Yeah, a part they should be different. I mean, normally if you just consider this algebra, a part you can think of them as a formal parameter. It's only when you have to relate to there's some concrete physical problems where you want to relate to other algebras, then there are some numbers, complex numbers. I mean, a priori you want them to be different so that they don't have any consolations.
Usually when we put a loop, we say it's an adjoint representation. Is that the way you would take it to be?
Yeah, but here I'm not talking about any physical. Yes, normally that correspond to adjoint. But now I'm not discussing any physical setup yet. So this is the symmetric quiver. Let me actually give another example. Another symmetric quiver that Piotr would like. So so then we have two vertices. So we will have 4 bonding factors. So we have so let's write this H1, H2. So for the chiral quiver, let's say H. Then, for example, for this case, the 3-loop quiver with a potential. So if we assign the weight of these 3 arrows, H1, H2, H3, this potential will give, so the two terms give the same constraint on this on these 3 weights. So it's H1 plus H2 plus 3 equal to 0. So now this is an example of the binding factor. Now let's try to write down these relations. So I think I erased this. I already write down the
Why did you write only 2 terms? There can be one more term, no? Also possible.
So there are 2 terms, and then both of them give the same constraint on each.
I agree. No, every term will give you a constraint, right? Because you're going to
Yes.
take it over a total.
Yes.
Around that vertex there are 3 such loops.
They give the same one. They give the same constraint here. So I think it used to be here. The mode relation for the first two. So the first 2 relation, they do not depend on quiver. It's just the last 4 that depends on the quiver. So now, so this is a bit trivial. Let me try to use this one to explain the mode relation. Let's look at this case. Let's look at the mode relation for percent E. So so we take the we move the denominator to the other side. So we have so now we expand. So then I have so this will be the mode relation. And then for the, let me also write down the, like I said, I don't need to write down the EE. So for the EE, you just replace all the 5s by E. That's another, and then for the F is, you just change the sign here for the,
before. Okay, you're already erasing all of
no, I use a line
okay.
here.
So if you want to write still some on this remaining part, then
Yeah, maybe I
okay,
use
okay.
this.
I will take this. Okay.
Yeah, maybe. Let me give one example that's relevant for the plane partition. So I want to show the example for this guy here. So So for that quiver, the bounding factor is this. With the condition H1 plus H2 plus H3 equal to 0. So you see it's S3 symmetric under this promoting the three HIs. So you can write it as in a S3 symmetric way. Let's define. So we can define this as a sigma 1 is 0, and you define sigma 2 and sigma 3. So so we don't need to look at the precise and EF relation. So let's just look at the precise E relation. So now you will have Z. And so this view. Now I want to expand this. So I will have so you see that there's these two parameters, sigma 2 and sigma 3. And you see that when sigma 3 equal to 0, this will become a Lie algebra. This is probably the most complete looking example that I'm going to show for the entire lecture. So this will be the algebra that's actually related to the 1 plus infinity algebra. So this is the diffeomorphism of the surface, and the sigma 2 and sigma 3 parameter. So okay, so this is actually a family. There's a 2-parameter family for this algebra. So there's a central charge and a coupling constant. And this the sigma 2 and sigma 3 will be related to these 2 parameters. And when sigma 3 is 0, that corresponds to a free point of this W1 plus infinity. So that's the point where you can realize this as a free formulas.
So sigma 3 is 0 when one of these h is 0.
Yes. Yes. So, I mean, this might be.
Or C is also 0. C is the central charge.
C is the central charge.
And that will be 0 when any
No.
one of the HI will be 0.
No, that's it's more like the lambda. Actually, it's also not the lambda, but I mean, it's I think the lambda will correspond to the 1. So this W1 plus infinity have two special points when lambda equal to 0 and lambda equal to 1. I think this is when you can realize by free fermion. This point is when you can realize by free bosons. But C is not 0. I mean, if C is 0, then there's no.
No, I agree. No, I thought you said C is a function of sigma 3. That's why I got confused.
No, they are, but that doesn't mean that
Both
C is.
C and lambda
Yes,
functions of
yes.
sigma 1, sigma 2 and sigma 3.
Yes, yes, yes. And another formulation that you might be more familiar with is a coset formulation, where you have you write it as a WNK when n is integer. So you write it like this. So there are 3 possible parameterization either in terms of nk or c lambda or sigma 2, sigma 3. So the formulation in terms of this is the invariant under the permutation of the h1, h2, h3. So that's actually it's some symmetry that's there, but it's not easy to see if you use the other formulation. So that's actually vaguely important for some other purposes. Yeah, this is the C3 example. I think if you understand this one inside out, you can do many generalizations starting from there. The building of the representations and the connection to VOA is all starting. I think this is the best example to study carefully.
That's the minimal model, right?
Yes, this is WNK mini model, exactly. So yeah, as maybe I just give you some teaser that maybe I explain tomorrow. That
okay, please wait with erasing that.
yeah, I'm really bad at using my Blackboard. Maybe I use this. This is not useful.
Yeah, this is fine.
So what's not clear from your approach is where is the level K everything shows up in your formal expression is not very visible.
Yeah, yeah, that's the whole point. It's not immediately visible. So so if you're familiar with this WNK model,
Yeah.
so
And please note that we should end soon. This.
Then we can take it up tomorrow.
Yeah, we can also start tomorrow.
okay, yes, yes.
But if you want to end some sentence, please feel free to do it.
Some sentence. So I think yeah, sorry. I wanted to. So this is all quadratic relation. You see that the quadratic relation is universal. You write it down and then you just plug in the information of the quiver. So the higher order, there are also higher order relations. I mean, for example, for the Yang-Mian, you know that there are third relations. So those are not that easy to fix. So you have to fix them for each case by case for each individual quivers. For example, for the alpha unit of GO1, you have cell relations. Like this. Also F. I mean, or in general, for the Yangmian, you will be you need to supplement by the higher order relations. So the way to fix it, it also you need to consider the representation. That also give you a procedure to fix higher order relations. But in general, it's not easy to write it down. And also, you also have to fix the co-product. I think this I'll probably explain on Friday. I mean, both these two, you need more information on the representation to fix. Yes.
Okay, thank you. Yeah, and please let me push the questions for tomorrow because we need to prepare for Lima's lecture.